Has anybody done performance analysis trying to improve the peak performance of their application? Anybody? Yeah. Right, that's typically what we're looking at when we're trying to make an application run fast is that peak performance. Has anybody worked on trying to tune startup of their application? Okay, yeah. What about warm-up? Okay. So when we look at a graph like this, though, there's really, easy to talk about peak performance because it's clear when we've sort of hit that final point of performance in our application. We can kind of talk about startup if we pick a point and say that that's startup. So in this case, if we look at this, we'll call startup the time it takes to get that first task, that first meaningful piece of work done. And then warm-up is kind of the vague area between startup and peak performance. So these aren't really well clear defined phases in your application. There's a little bit of a spectrum and fuzziness around this. So what does this have to do with Project Leiden? Well, Project Leiden is looking at improving the startup and the warm-up of Java applications. So if we don't know what startup and warm-up are, we have an awfully hard time improving them. So as we said, startup's the time to do that first useful piece of work. That's that first request on your server application. And warm-up is the time it takes to sort of get to that stabilized peak performance. Now work is done both by your application. Your application at startup is probably reading configuration files. It might be scanning the class path to find annotations. It might be opening sockets and creating loggers and more loggers. And the JVM is doing work on behalf of your application as well. We're loading the class files you ask for. We're resolving constant pool entries. We're JIT compiling code. We're running the verifier to make sure the code you're running is safe. So there's a lot of things that are happening from the JVM perspective to help get your code to run fast, in addition to the things your application is doing. And the reason we care about startup and warm-up is because Java's highly dynamic. Okay, so we tend to think about Java as being a static language, right? We talk about Java is statically typed. But the problem with static and dynamic is that they're really very abused terms. So let's pick kind of a vague definition that matches what a lot of people think about, and we'll use that and kind of work through that and through a couple of other definitions and see if we can get to a sort of a meaningful understanding of dynamic and static, at least for Java. So if we said Java has, if we said static means compile time and dynamic means runtime, is Java statically or dynamically typed? I can't really ask you the question because the answer is on the slide. So the answer is yes, right? Java has a static type system. The Java language compiler, Java-C, will run your code and type check it for you. And it's got a pretty powerful type system. It's got generics in there. It's got checked exceptions in there. It's got definite assignment analysis, overload resolution to make sure the types match the method you're wanting to call. But it also has runtime type checking. Array store exception, making sure you're putting the right typed thing into an array. It also has runtime casting, check cast. So what we see is that Java is both statically and dynamically typed. As an interesting aside here, the type systems of the static, or the static type systems in most languages tend to be a more powerful type system than the runtime type system. So it's a common pattern you'll see with languages. But what we see here is that we can't just say that static means compile time and dynamic means runtime. So let's check the dictionary to maybe see if we can come up with a better meaning for what static versus dynamic is. So if we take a look at the definitions of static, we see things about without motion. We see bodies at rest, equilibrium, little change. So maybe static means unchanging. And if we look at dynamic, we see continuous and productive change in that definition. So maybe static's unchanging, dynamic is changing. Let's run with this a little bit and see what we get. So if we're going to talk about changing versus unchanging, then we should talk about what is changing or not changing, and when is it changing or not changing. So if we look at Java, we have a lot of things that are dynamic. dynamic typing, array store checks and casting. We have dynamic class loading verification. All of these happen at runtime. Dynamic class redefinition. So classes being changed at runtime again. We have dynamic compilation, where we compile something and maybe where we even for some reason we recompile it or we throw away the code that we have because some assumption's been violated and we have to de-optimize. Java also has dynamic linkage. And we don't often think about this, but all of our Java programs are wonderfully dynamically linked, right? In one class, when we want to talk about a field or a method in another class, we just use a symbolic name and some symbolic descriptors to be able to make that connection from this class to that class. And the first time we go to run that code or access that field, the VM has to go do a bunch of work to make sure that both classes exist, that the access control works for being able to talk to them, that the field or the method exists, that it has the right parameters, and that everything works. And so the VM does a whole bunch of work to make this linkage, but it does this on first use of each constant pool entry. So we do some expensive work, but we do it once per constant pool entry. Java also has dynamic introspection, instance of reflection, dynamic dispatch through virtual function tables. So we've got a lot of dynamic things that are happening that are part of what is changing. So we're pretty dynamic. Okay, so if dynamic is what is changing and not changing, maybe we need to look at what period these things are changing. Right? We often say, as we said earlier, compile time versus runtime, but that's not really sufficient to really model when things change or when they don't change. There's a lot of interesting phase transitions that happen on smaller granularities inside Java. If we look at this code, it says static final int seed, and then it goes off to some hardware random number generator to get its value. So is this static or dynamic? It says static, so it's a good place to start. But the initializer for this field runs at runtime. Well, that kind of sounds dynamic. But the variable's value, once it's set, is unchanged, right? From the point where we set this in that class initializer to that class is either unloaded or the JVM exits, we're unchanging, we're a single value. And none of this really maps well to compile time versus runtime. And interestingly, the JVM likes to take that final field, and if there's other code referencing that, rather than going off to fetch that each time it references, it grabs it once, embeds it into the compiled code, and uses that to optimize throughout. So Java's really good at treating things that were born dynamic as though they were actually static. Okay, so what we see here is that static and dynamic aren't only opposite ends of a spectrum. Java doesn't say you get one and you have to give the other up. Java says, hey, let's take both. And then it's going to reason about the things that you have, the dynamic behaviors, and try and treat them as statically as it can at runtime to give you the best possible performance. This is a core competency of the JVM. Right? We see this with static field initialization. That's a dynamic initialization of the field, but we can treat it like it's static after that. We see it with class loading. Classes are loaded dynamically, but once loaded, that class, that relationship to that name is static after that. And we see this with many JIT optimizations as well, being able to take things that were born dynamic and optimize them as though they were static. Now, the JVM not only does this kind of optimization, it also does it speculatively. So Java says, hey, this thing looks like it might be static, so I'm going to assert that it is static. But I don't want to take away your ability to dynamically change that later, so I'm going to have to do something to allow fallback optimizations. One example of this is an interface call. If you have only a single implementer of that interface, Java doesn't make that invoke interface call through the compiled code. What it does is it inlines the single implementation because it knows every time you do an invoke interface, it's going to go to that implementation. And this works great, you get good performance, right up until somebody loads another class that also implements that interface. And now that code that we had earlier may not be valid anymore. And so we need to go back and de-optimize so that we can re-optimize later. Java also does a whole bunch of profile-driven de-optimization as well. So we're seeing this we're seeing these things born dynamic, treated as though they're static, and Java being able to do this speculatively so it can back off and say, I can hide the evidence of the optimization I made if it turns out I was wrong. Okay, so why does this matter for startup? When we talk about the activities that happen at startup, they're done dynamically, right? We're reading those configuration files that your application is doing. We're scanning for annotations. We're opening sockets and registering listeners. We're creating loggers. And the JVM's doing all the activities that it does on your behalf dynamically each time. So we're loading classes, we're reading them from disk, verifying them, creating internal metadata for it, running static initializers, we're interpreting those bytecodes as we go along, gathering profiles, linking call sites, resolving constants, and we're doing all of this at startup. So startup has a huge amount of work going on just to be able to get to that first useful piece of work. What about warm-up? Well, as we said earlier, these things are spectrums, so a lot of the work that's happening at startup continues to bleed into warm-up as well. But in addition to that, your application starts to populate caches. As more requests come in, it's able to say, oh, I've seen this before, I can cache a piece of this so I can reuse it later. It starts to do other kinds of activities to be able to speed up the operation of your program. And the JVM continues to do things on behalf of your program. In particular, it does JIT compilation. Right, we start to recognize, if you were here for Doug's talk earlier, he talked about recognizing the hot pieces of code and being able to optimize those. And that's exactly what the JVM does. It recognizes which pieces are hot, tries to compile them as much as it can, and tries to compile the hottest pieces at even higher tiers and with higher levels of compilation. Okay, so this sounds like a lot of work that gets done over and over and over again to allow the JVM to hide the dynamic nature of the application. Why do we do this every time? It seems really inefficient. Well, and the answer is we do it because you as developers actually love that, right? It allows us to write really expressive code. It allows us to use reflection and dynamic features. It allows us to load the classes as we need them and not load them if we don't need them. It allows us to write more expressive programs. And we all like it when we can compile an update to our jar file, drop it on our running class path, and rerun our application and pick up the new classes. We don't want to have to do long, slow compilation cycles. Additionally, this dynamic compilation gives us better code. So we get a more expressive program and we get a better optimized program. Because that JIT that's running and finding those hot pieces of code is able to take the environment into effect and into account when it's doing that compilation. So it knows, hey, you have a 4 CPU system, you have these vector instructions, you have that set of instructions. We're able to profile based on the exact behavior you're doing with your application, and then we can optimize based on that or re-optimize if the behavior changes. So all this dynamic behavior and treating this dynamic behavior as static gives us great startup and warm-up. It also gives us better tool integration. It's easier for tools to integrate into this world because we have this dynamic nature. And this trade-off is actually really good for most applications. If you're running some kind of longer-lived application, you're typically focused on that peak performance. And so being able to get these dynamic benefits and still get that amazing peak performance is really good. It's what you want. For some other applications, maybe you're writing a command line tool, the peak performance is less important. You care much more about startup or warm-up because maybe your application doesn't do that much work once it starts up. So there's trade-offs here. All right, so let's revisit our startup and our warm-up picture. Now let's think about what's happening and how long these sections of time take. So that first yellow dot is our typical work. The green line shows sort of an idealized version of what this is. And if we look at the time between the yellow and the green lines for that first useful unit of work, this is a lot of class initialization activity, as we said. And this is usually measured in CPU milliseconds. So startup is actually reasonably fast, or it takes a reasonably small amount of CPU cycles to get there. And then we have our warm-up, which is the rest of the difference between these two curves. And this is often characterized by the online JIT activity. and the time it takes to stabilize at our peak performance. And this is usually measured in CPU seconds, right? So startup is a very small period of time. Warm-up is a longer phase of time. Now, to improve these though, we have to find some way to push that first point down, right? And to improve warm-up, we have to push the rest of the curve down. So that's really what we're looking for, is how do we improve these two phases of our application. Now, if we want to improve these, we have to move the work somewhere. Erin Schnobel gave a talk yesterday, I don't know how many of you were there, where she talked about architecture. And one of the examples she used in that was P, right? And you can push the P's around your plate wherever you want, but they're still there, right? Somebody has to deal with them. It's a certain amount of complexity that just has to be dealt with. And so when we want to improve startup, we have to shift the work somewhere. We can't typically just say it doesn't exist. So one way we can do this is lazy initialization. That shifts it later, that moves it off that critical path. And maybe we shift it far enough that it never actually gets needed by the application. Great. Maybe we can shift things earlier. We can pull them from runtime to build time. And what we want to be able to shift is not just the JVM's activity, right, the work that it's doing on your behalf. We also want to find ways to shift what the application is doing. And if we look, though, there are a lot of things that the JVM already does to shift computation. So let's dig into that a little further. So Java's got a lot of features that can shift compilation. Again, I don't know how, if you were at Doug's talk earlier, he talked about constant folding that Java C does, right? If we want to add 2 and 3 together, Java C doesn't do push 2, push 3, I add, and then store the result somewhere. Java C does the 2 plus 3 compile time, figures out it's 5, and stores the 5 somewhere, right? And that's perfectly valid. It's perfectly within the spec to be able to do that kind of constant folding. And that's a shift to earlier. Garbage collection, on the other hand, is really a shift to later. Rather than having to free or reclaim the memory when something goes out of scope or is no longer referenced anymore, we get to free it at a time that's more opportune for the program. Lazy class loading and initialization is a shift later. But this one's really interesting. If you've spent enough time reading the JVM spec, lazy class loading isn't actually required. The JVM is free to load things earlier as long as it only reports the errors at the points where they would naturally occur in a program. So there's a lot of fuzziness and flexibility here already on what a JVM is allowed to do. It's just about when it has to report to you what it's done if something went wrong. Now, some shifts require user input, right? Java 9 had an experimental AOT ahead of time compiler, which would take a module, compile the entire module, and give you a native library that was able to run that code. And that required some level of opt-in from the user to be able to do that ahead of time. CDS is able to take pre-digested class files that have been turned into the VM internal version of metadata and reuse them from one run to the next. So that's a shift to earlier as well. And these shifts are all valid, provided that the program meaning is preserved, right? We don't want to shift something in a way that changes the meaning of your program. That would be really scary. All right, so Leiden is going to focus on how do we expand the set of options we have for shifting things. So some kinds of shifts we can do without changing any of the specification. This could be taking Lambda expressions and converting them to byte code at build time. That's an earlier shift. Or we could speculatively compile ahead of time code. Others may require some kind of specification change. If we wanted to say, remove dead code or methods that we don't think are going to be called, which is called stripping, we probably don't want to do that without having the user opt in. Yet other features may require new programming models. So whether that's lazy static final fields or computed constants, which we'll talk about later. Now, What about constraining dynamism? We said earlier, part of the challenge in this space is that so much of the behavior is dynamic. So that maybe one way to solve this problem is to find ways to constrain that dynamic behavior and to give the JVM more freedom to optimize based on those constraints. So those might be things like saying, look, I'm never going to install an agent. I promise you this. So I promise you that the following classes will never change once they're loaded. That might be a constraint that enables the JVM to optimize further. Some programs might be able to accept even more constraints if they get enough benefit, right? So we're talking about trade-offs here. Some of these constraints, we can add them, but you might have to, and you might get better performance, but it means you've given up something to get that. Some programs have, opted into the ultimate constraint, which is the closed world assumption. And with that, you could compile things down into a very small executable that only runs exactly what's there. But you have to sort of give up dynamic class loading. You have to limit reflection. There's a bunch of constraints you have to take on to be able to get there. And not every application is going to be able to or going to want to. So Leiden says, we recognize that there's a spectrum here. What we want to do is give developers the options. We want you to be able to choose where your application fits on that spectrum, what you're willing to give up, and the gains that you can get by doing that. All right, so what are the values for Project Leiden? So we will shift computation temporally, both later and earlier in time. Later in time in the hope that it won't be necessary, earlier to move things from runtime to build time. We will constrain Java's natural dynamism if necessary to enable more and better shifting. So we're gonna introduce a spectrum of constraints on computation because shifting well often requires static analysis, and general static analysis is hard. We will do these things selectively. We're going to allow you as a developer to opt into the constraints you want to accept and which computations you want to shift. And we're going to do all of this compatibly. We want to evolve the Java platform spec as needed to permit this shifting and constraining, while also finding ways that we can shift and constrain things that don't need specification changes. Okay, so let's deep dive into one of the techniques that we have for shifting today. And this is CDS, or class data sharing, which we have retroactively renamed to cached data storage because there's a lot more things that we could store here that are useful. So CDS was introduced in JDK5, and what it does is it takes class files that have been loaded and parsed and turned into the internal instance class metadata representation and says, I will take that and I will save that away so that I can reuse that later. And it does this for the core classes, right? Because whenever your JVM starts, there are certain classes that you need: object, string, class, class loader, thread, module now. Every run is going to need this. So if we take those and we store these in a pre-cached version, we're able to warm up, thank you. We're able to start up faster because rather than having to do this work every time, we did it once. But we've taken CDS that we had in JDK5 and we've continued to evolve it over the years. So as of JDK8, it can cache generated Lambda proxy classes. As of JDK10, it was extended beyond just what was in the system classes to allow application classes as well. And JDK12 said there are certain pure objects that are cacheable too. The module graph is a great example of this. The integer cache is another. So CDS is going to be, it has been, and it will continue to be a key tool in what we're able to do, because there are a lot of other things that we can cache, maybe profile data or compiled code or other things as well. So before I dig a little bit more into how AppCDS works, does anybody here use AppCDS? Okay, so not many. So the way AppCDS works is kind of like a shared library from C or C++. It's created at runtime, And it creates this archive that has these cached classes in it. And they contain the metadata that the JVM wants to use. And these get, by default are the ones that are loaded by every run. But alternatively, you can create your own cache file that has different classes in it and can include your application classes. All right, so what does it look like when you want to use AppCDS? So to use this today, we do something called a training run. So that means you take your application, you run it, and you give it this option -xx dump loaded class list. And this dumps out the list of all the classes that were loaded. The nice thing about this is it's a text file, so you can merge multiple of these lists together to get the right set of classes that you want. And then you create your archive. So you pass a couple of options to do that. You say -x share dump, -xx shared class list file, and give it the class list, and -xx shared archive file, and give it the name of the file. And this will run and pre-parse your classes, store them away in that kind of pickled state to be able to reuse later. And then when you want to use them, you run with -xx shared archive file. So what does that workflow look like, right? We run the application, that's our training run, we collect some data from it, we use that to optimize later runs. So if we look at the kind of improvements we get, if we turn off CDS and we just start the JDK and these numbers, the actual numbers themselves don't really matter, it's about the orders of magnitude here because this was run on somebody's laptop. So with CDS disabled, it was 300 milliseconds. When we used the default CDS, it was about 260, so we shaved off about 40 milliseconds. And when we used AppCDS, with this test application of Java-C compiling a single file, we cut that time in about half. So what we have is a tool today in the JDK that's actually quite useful for improving startup. And we may package this eventually as a condenser. Condensers are one of the workflows in Leiden, and we'll hopefully touch on those later in the talk. All right, so to do this though, we said AppCDS requires a training run. A training run is some run of your application, usually by some small driver program or maybe by an integration test, that takes your program and runs through the common workflows that you would care about during startup and the warm-up. And it exercises those code paths to find which classes get used, to figure out which methods get compiled, to figure out which things get profiled. And we use that to be able to observe the application because that dynamic observation gives us more powerful information than just the static analysis. And training runs are going to be an important part of our startup improvement story. And they're effective for some of the same reasons that dynamic compilation is effective, because it allows us to see what's actually happening in the system. Right? It's this Java's superpower of observing what's happening to optimize based on that. All right, so if we look at the way CDS works today, you've got your shared archive, and at some point your program issues some kind of load class directive or some kind of define class directive. And it says, hey, please define me class foo. And so it goes off, and the VM recognizes this, goes off and checks CDS. And if it has your class already parsed in there, it's able to take that and load it. And great, we saved doing the work to go off to the file system. We saved doing the work to do some of the parsing and verification of this. Now we just have the class and we're ready to go. Great, so we can continue on. And then the next define class operation occurs for another name, and we go off and check CDS, and yes, we have that class so we can pull it in. So we've been able to cut some of the work out of here, but we're still loading these classes on a request by request basis. And there are still things that can happen that can invalidate these things, right? So it's a speculative optimization. If something changes in your system that says this no longer applies, then we won't use it. Okay, so we have to take another bit of a digression to look at what happens before main runs. Java has what's called a launcher. So when you run Java dash, CP of some class path and my main class, what's happening is there's a launcher application there. And this launcher is typically written in C or C++. and it's used to create and initialize your Java VM. Has anybody ever written a launcher? Yeah, I was going to say very few people. If you're interested in a lot of the details on this, you can look at Chapter 5 of the JNI specification. It covers something called the invocation API. But what you need to know from this slide is that there's a method called JNI create Java VM. And it's responsible for setting up and initializing your Java VM. So it allocates native memory for it, it configures the interpreter, it initializes the garbage collectors, it starts the JIT threads and the garbage collector threads, and it loads and initializes a whole lot of classes. Right? I can't go and load your main class until I know about class. And I can't know about class until I know about object. And I can't load any classes till I know about class loader. And everything needs strings, so I need string. And I need some thread to run that code on, so I better have thread there. And now I need to have a module for all of those classes, so I better have modules initialized. And each one of these classes wants to use other classes as well. So there's like a wave that comes out from this of classes that get loaded and initialized before we ever go and look at your main class. So all of these are part of sort of a conceptual phase of time that can be thought of as pre-main. This is the set of actions and things that happen before main. And even before we go off to load your main class, JNI create Java VM returns, and then this launcher program is responsible for using regular JNI functions like find class to go find your main class, and other JNI functions to locate that main method. It used to be very easy to locate the main method. It had one signature, but with the introduction of instance main, main can now have multiple signatures. So finding that method has become a little bit more complicated as well. But what's interesting here is we started with CDS that loads these core classes that the JVM always needs. And now we've said there's also this pre-main phase where all of these classes get loaded. And this pre-main phase is not a single method. There's no method in your Java source called pre-main. It's just a phase, a concept that encapsulates a set of actions, right? These are the class loading and initialization, JIT compilation, garbage collection that's happening before main ever gets called. And we said CDS is responsible for shifting assets from training runs to deployment runs, right? It's able to shift that class metadata and some heap objects, and maybe more things in the future. But what if we took these two concepts and we put them together? Well, we did. There's a JEP draft called loaded classes in CDS archives. And the idea is, rather than storing these classes in merely a pre-parsed state where we still have to take them and do some work to adopt them, what if we stored them in a live state? So these classes are not something that we have to then individually request and wire in, but something where they live as though they're fully set up and ready to be used inside of CDS. That means that rather than having to wire them into their superclasses and their interfaces at runtime, they're already pre-wired. So that means that they have a stable identity inside of CDS. It also means that we've saved the class mirrors, the class objects away in CDS as well. And so what that means when we marry this idea with pre-main is that rather than our CDS archive holding things that we parse in one at a time on load class optimization or on load class calls, we bring them all in at once. So JNI create Java VM happens to start and initialize your JVM, and we take all of those classes that we identified in our training run and we adopt them wholesale into our system. And we adopt them as live stable classes. They have live identities. And they begin life in a ready-to-use state. So this is a bulk loading of what we recognize from our training run. And what's interesting here is that we're able to do this with what we have in the JVM spec without really having to add any new constraints. The only slightly minor constraint we've had to add to do this is to say that you can't get a class file load hook for these classes before they're loaded. So you can go off and modify them later, but you don't get that very first kick at the can. So a very minor constraint for a fairly big win. and this win is a foundational win. So it's one that we're able to build other interesting things on top of. Right, once we have these stable addresses, now we have an easy way to say this class had that profiling data in the training run. And so in our deployment run, we can say this class can reuse that profile data. We can say this class has this, we compiled these methods in that class, so maybe we want to compile those methods as AOT code and reuse those in our deployment runs. So we're starting to be able to build up other optimizations based on being able to adopt these classes in bulk. Okay, so with this pre-main concept, with CDS, with the features that we already have in Hotspot, how far can we get without imposing new constraints, without having to make spec changes or give up the dynamic behavior we talked about earlier? Well, to answer that, we have to look a little bit at how code is JITted during startup and warmup. I have a very pretty picture that I stole from a colleague that shows a slightly simplified version of the life cycle of a Java method. It starts out in the interpreter. And in the interpreter, we're able to collect full profiles for this method. And after some length of time, we go to tier 2, which is done with the C1 JIT. I understand that's confusing. I get it wrong all the time. And we do very little profiling if we ended up in tier 2, mostly profiling on entry. Then a method may go to tier 3, which is also done with the C1 JIT. And there we do full profiling. And then a method that has been fully profiled and is ready may get compiled at tier 4, and this is done with a different JIT, such as C2, and there's no profiling that's done there. So let's take a look at sort of the same information with some words here. We see the interpreter starts, it collects full profiles. Tier 1 is done with C1. It's only used for the simplest possible code, so it gets very little use because it does no profiling, because the code there wouldn't benefit from profiling. Typically, this would be if you were going to compile a getter, but you don't usually do that. You would just inline it and whoever is going to call it instead. So tier 2 is sort of simple code with profiling on method entries. This is often used when the profile queue gets over full and we don't have time to profile everything. We want to get you out of the interpreter and into compiled code, but we don't want to spend as much time generating the profile information that we need. We just want to get you going. And so we just do entry-level profiling there so that we can later upgrade you. Tier 3, full profiling, spins up fairly quickly. And all of this is because we want to identify what the hottest methods are so that we can get you into tier 4, which benefits from using that profiling information, but doesn't collect any. And tier 4 assumes by the time you get to this point, all the classes that you need have been initialized. It also says, hey, if there's some input that's awkward that I didn't expect based from my profiles, I can de-optimize and re-optimize later. And if I have to do that, I can always re-profile to figure out what I should be doing before I re-optimize. So we have this tiered compilation scheme that recognizes that there's this phase shift from startup to warm-up. So startup is typically handled by the lower tiers, often with the interpreter, because it needs to do the symbol resolution. It needs to run the class initializers. It needs to find all your classes. Warm-up, right, after that first useful phase of work, is when code is shifting from those lower tiers into the higher ones. Right? First, we have to gather profiles of what your application is doing. Then we have to use those profiles to generate the tier 4 code. And this takes some amount of time. And we sort of stabilize at our peak level performance when the application behavior stabilizes and the JIT compilation has stabilized compiling all the hottest things at that tier 4 code. Now, what's interesting in this scheme is that it tells us that we probably don't want a single version of AOT code. Because if we can only have a single version of AOT code, that code has to handle the worst case of those lower tiers. And that means that that AOT code may not be useful for later tiers. And so we have to think about what kind of tiering strategy might we need with AOT so that we can get the same kinds of benefits that we've always gotten. And this JIT compilation is speculative. We're always free to toss the code. Maybe the environment has changed. A new class was loaded, as we said earlier. Maybe the profile data we used to generate this no longer matches the observed behavior. Maybe we just ran out of space in the code cache, or somebody attached a debugger and we have to throw away the code. So all of this JIT optimization is a pure optimization, one we can do or undo or not do, and that's fine. So to make this work well in our system, we're going to need to apply those same kinds of reasons and rules to whatever we do in Leiden. Now, the experiments we've done so far have been focused a lot on teaching CDS new tricks, right? The CDS of today uses pre-pickled or pre-parsed classes and metadata, and we've already introduced ways of taking those pre-parsed classes and turning them into fully live classes that we can use, right? That loaded classes in CDS archives JEP gets us there. And what's interesting is we don't have to just do class-to-class relationships. That means we can also resolve constant pool entries, because we know the classes that are going to be used, so we can pre-resolve class-to-class references, field references, method references there, and that lets us take some of that work that would have otherwise been done as startup and shift it into our CDS archive. Now, we can extend this further. We could take profiles that were gathered in tiers 0 to 3 and store those in CDS as well. We could take compiled methods and store those. We could link invoke dynamic call sites or pre-initialize sort of specialized classes and be able to save those away. And then, because this is speculative, we'll have some set of checks to make sure that the things we've done still fit and still apply, and we can throw it away if it doesn't. All right, so what this means though is now we have options. We have our CDS with loaded classes that have stable identities. We might have profiling data in there. We might be able to put AOT code in there. So we have options. We can take that profiling data, and maybe at startup what we want to do is use those profiles and just immediately JIT all those methods. And that gives us, maybe faster warm-up. Or maybe we have pre-compiled code that we want to load. But we saw earlier that pre-compiling code may not be sufficient if we only have one version of it. Right? Just as the JIT compiler goes through different tiers and stages of the code that it uses the speculative AOT may need different tiers as well. Maybe we need AOT code that is compiled for very fast versions, so C2 code, with class initialization barriers left in that code. And then we need another version of that code that's compiled with C2 as well that doesn't have these class initialization barriers left in there. And then we need some kind of policy that says, hey, we've run this enough that the barriers have all been triggered or something else has happened, and we can swap from one phase of this to another, right? We've added a new set of tiers into our tiered compilation. But all of this AOT code has to remain speculative. We're caching based on behavior we saw in our training runs, which is better than trying to use static information because we didn't have to introduce any new constraints. We're just doing what we saw the application do before. And we're doing this all speculatively, which is hotspot superpower, which allows us to use this code and maybe some assumption baked into this code gets violated. So we throw this code away and we re-JIT. Right? We're not forced to just compile various flavors of AOT and only use AOT. Because Java is dynamic and we've adopted that dynamic behavior and we love that dynamic behavior, we can actually continue to use it. Maybe we use the AOT code to get a ways, and to get to the very highest peak performance, we use the JIT compiler at runtime. There's a lot of options that can be done here and a lot of adaptation that we can do. The biggest challenge here is figuring out the policies to govern when to move from one kind of code to another. So let's dig into a couple of case studies. This one is Java C, and it is compiling 100 small source files over and over again. We see our yellow line is our baseline without Leiden, and our red line is using some of the experiments and prototypes that we have in the Leiden repo. And what we see there is about a 2x startup improvement. and a warm-up improvement, and all of this without changing any of Java-C's code. We just did some training runs, recognized what was being done, saved away some profile data and some AOT code, and put this into a specialized CDS archive. So we got basically a 2x startup improvement for free, all by shifting work earlier in time using CDS. And we didn't really have to add any new constraints. But there's no single magic bullet here. We had to take several techniques and map them together and let them form a virtuous cycle to build on top of each other to get us to where we needed to go. Now the tricky thing is this machinery doesn't tune itself. Just like Hotspot itself, there's always a lot of work to figure out how to build the policies in place so that these things can be done automatically for you and done efficiently across a wide variety of workloads. So let's take a look at a second case study. This is XML validation, which is done from spec JVM, and we see a fairly significant startup improvement here. But the warm-up is basically unchanged. Again, we didn't have to change any of the existing code, but what this tells us is that startup is the only interesting win for that particular workload. Warm-up may be okay for smaller applications. It depends on what you're doing, on what techniques you're going to want to apply, what pieces you're going to want to use, and what kind of benefits you're going to get. And in some of these benchmarks, it's kind of hard to tell when we've actually hit stable peak performance because they're fairly noisy. All right, I have another case study here. This is everybody's favorite small application. And we see the first bar here. The tallest one is using a fat jar. The next line is taking that fat jar and unpacking it onto the system. After that, it's saying, okay, let's just use a default CDS. And then it's using a dynamic CDS with the Leiden features built into it. And then on top of that, Spring has a AOT tool that's able to make the code in Spring a little more amenable to AOT. And so if you run that as well, you can get even more improvements out of this. So what we see here is a 4x startup improvement, and we didn't have to change Pet Clinic at all. We had to do some training runs, we had to adapt CDS, we had to make some hotspot changes, but we're able to take applications and get significant startup improvements without having to make code changes to those applications, which is a little surprising, right? What we see here is that there's a lot of tactics we can use. Some of them give us big wins, some of them give us smaller wins, but they all work together. That early class loading via CDS is a big win. Cache and compiled code is a fairly big win. Resolving invoke dynamic call sites is a smaller win. Clever tier 4 code that contains class initialization checks in it was a bit of a smaller win. And Spring Boot's ahead of time configuration tool was a pretty big win. What's interesting about that tool is it scans your class path to find the annotations at build time and generates the components to hook things up more quickly at runtime. And this is basically what we're calling a condenser, which I'll touch on in a couple of slides. So what we see here is that time-shifting speculative optimization works. We're able to get a lot of the benefits that we want without having to give up compatibility, without having to give up the dynamic behavior of Java. We didn't have to change the programming model. We didn't have to change the specification. We got to have our cake and eat it too. We just had to make some rearranging of existing hotspot components, and we had to do training runs. Now, there's some work still to be done here to make training runs a little easier to do and a little friendlier for working with. And we have some more work to do around tuning and policy work here, but we've taken the first steps on this path. Now, I've mentioned condensers a couple of times. Is anybody familiar with JLink? Okay. So JLink is a tool in the JDK. It was introduced in JDK 9. It takes a set of modules and converts them into a JImage file. And JLink has a bunch of plugins that you can opt into using there. And they can do things like compress the classes, they can strip debug information. So there's different things you can opt into there. And when we started this project, we thought that kind of approach was going to be sort of the driving factor of what we had to do. But we've been so impressed with the sort of unreasonable effectiveness of training runs that they have taken center stage on the work that we're doing, and condensers have kind of stepped back. Now, there still may be a place for condensers. This may be a application-specific piece of the story, like Spring's AOT tool. But there may also be ones that eventually come from the JDK as well. We'll continue to experiment and see what we need to do there. The key thing with doing something like condensers is that we need to make sure that we didn't change the meaning of your program when we run them. We need to make sure that they compose together because they're going to be selected by users. And so they also need to be selectable because some applications may want to run them, some may not. Some deployments, right? If I'm running on my desktop, I may not want to run a bunch of tools before I can go and debug my program. So there's sort of different phases and different spectrums here as well. Now, one of the other pieces of this story that I haven't talked about yet is computed constants. We talked earlier about lazy static final fields. And the JDK has something for internal use right now that's kind of like that. And it's the @stable annotation. But this is an internal annotation. And when you mark a field with @stable, you're making this guarantee that I'm not going to change the value once I set it. And so it's the kind of guarantee that the JDK can make to itself, but it's hard to expose beyond that. And the JDK uses this to be able to say, look, I may not know at class initializer time what this field should be, but I'll know later. And when I set that, I promise I will never change it ever again. And so the JDK says, okay, I can trust that, and then I can compile that in and treat that like a truly static variable. So we need some way to take that behavior and expose that to users. So there's a draft for this as well called computed constants. And it looks at how do we expose the @stable power, that optimization, to user code. What I really like about this code is that it takes what would be a static final field where the behavior responsible for setting that field was sort of intermixed through everything else, and it moves it into a self-contained piece of in this case, a lambda. So you can look at it and say, this is the code that's responsible for setting that field. And that makes it much easier to reason about the side effects and the behavior of what's happening here. And so what this works for today is for shifting code off your critical path to later, but we may be able to find ways to recognize these patterns and shift it to earlier as well. Maybe there's another version of CDS that we can do that's able to save some of this value away for you. All right, so that's a lot of information, but there's a lot more to do. We need to continue to explore ways to shift our computation, right? We've got some JEPs in the pipeline around speculative optimizations around this loaded classes in CDS archives. We've got more pieces that we're looking at around training data and AOT code and the different possible tiers and phases we may have there. We have work to look at for the ergonomics of training runs. Maybe we need to introduce condensers into the Java platform to make it more amenable to doing these kinds of optimizations, just like the Spring AOT code. And maybe we need to find ways to bring shiftability into the programming model as well, so that you as a developer can tell us what you mean and where you want that code to run. Lots of experiments under the way, lots more to do. All right, so got about 5 minutes. If anyone has any questions. Yeah.
The Spring AOT improvisation that you were mentioning, right? Are they coming out in box with Spring, or is there anything that we have to do to get there?
I think that's
how do we, more than my question, how do we make it predictable, right? How can we make the learning improve is it for runtime or for the compile time?
So the Spring AOT tool runs over the class path that you would have used at runtime and finds the annotations it would have found at runtime and generates code that says, rather than doing the class path search, here are the annotations you need. It does sort of a pre-wiring of things for you.
So the bytecodes already gets them beforehand.
Yes.
Well, compilation, during the compilation it takes it. When does it take it?
So it's an extra tool you run over your classes. Yes?
Is Project Laden really geared towards the hotspot JVM, or is it going to be brought to kind of all the JVMs?
So Project Leiden is focused on startup and warm-up, and hotspot being the reference implementation, that's where we're going to do the work. If other JVMs want to partake or want to join in, great. But in terms of where we're going to do the work, it's going to be in hotspot.
So that would be like a part of the JVM spec. It's going to be like a new campus if you want.
So there may be specification changes, but the work that we've done so far hasn't required spec changes. It's just been a restacking of the components. It's been a recognizing of the behaviors and the things that we're allowed to do. And so other JVMs are free to do the same kinds of things. Yes?
With the CDS archive in place, is that, given that things are already aligned, I assume there's no class verification happening on those things. Is that something that you have to worry about?
So the question was, is there no class verification on CDS archives today? And the answer is, my understanding is there is some class verification that still occurs. So there are pieces of verification that don't have to occur because we've already done, making sure that the method doesn't overflow or underflow. But there are relationships that still need to be checked between classes.
I'm going to go with the obvious one. So you showed us the graph of the good stuff where you got down to the top of the AOT and further down. So you've done that work. When does that actually end up in OpenJDK?
So a lot of that work is in the OpenJDK Leiden repo today. We're working on taking that from something that runs well in tests and in the small experiments we've done to something that is stable, production ready, and that we believe has got all the right features to roll out. So when it's ready, which is always the unpleasant answer.
But when?
Yeah, I know. So.
If you had to spec
The basic CDS one, what is the confidence level to use the basic CDS in production?
CDS is shipped and used every day, every time you run the JDK. You should take the CDS that we're using today, use app CDS, and do it today in production, 100%.
Yeah, it's a very, so the way also it works is that if it's unable, like let's say there's something wrong with the CDS archive or it's not there, whatever, then it will just load it from the class file, or from file system. So it's like, you're not going to potentially have a production issue just because it didn't actually load properly. So that's one of the really nice things.
Yeah. Speculative optimizations, right? So we can use it or not.
Yeah, so you were mentioning some of the speculative optimization that you could use at runtime, and a lot of your data is on startup time. Do you have any examples of being able to use that data, like, again, after startup to improve application throughput or whatever your metrics might be?
So the question was, do we have data showing or reusing that profiling data to get better throughput? And the answer to that is Leiden is focused mainly on startup and warm-up. Hotspot already has really good throughput. So peak performance tends to be really good. It's a question of how quickly can we get from nothing to peak. And the goal of Project Leiden is to help shrink the time from starting to peak performance.
So this ahead of time compilation, if you have a previous day's run, I think there was some initiative within ADK to be able to save from the previous day's run and then start from the compile passes. So is that likely or is it not?
So there is also another project that's doing some exploration called Project Crack, or Coordinated Restore at Checkpoint. So it's a variation that uses the Linux CRIU to be able to take a snapshot of a process and then restore that later. There's investigations and work going on there as well to see how safe and how applicable that model is.
So, like, how far with Heidinga can we go with like some of the training runs? So, like, let's say like the Spring Boot clinic example. Like, should using that example, like, should we have like some sort of standard test to run to generate data to like see what hot methods there might be or something like that? Like, how would that work with some of the training runs for Heidinga?
So the question was about training runs and the data that we put into them. It's a great question, and it's an area where we're still exploring. Some things you may want to run your application at build time. Maybe you have integration tests that do this today, and that gives you a good enough set of data that we can use that to optimize your startup and your warm-up. For other applications, maybe you want to write something specific to drive them to get to those states. But there's still a lot to explore and to figure out in this area. Yeah.
Are you seeing any gotchas with when you're storing the fully loaded classes in memory? Like, for example, like with Firecracker, where you're doing like, you're saving states and JVM with random number generators. Are those limitations, or are you early enough before any of that's started?
We're early. So the question was, are there limitations around random number generators and things like that when we store classes into the CDS archive? And the answer is we're before class initialization. So we're early enough that that's not an issue yet. We're still going to initialize those classes at runtime.
Okay, and that's even the expanding on you're saying, hey, we're going to take this a little bit further, that you're still talking about class initialization now. Yes.
Okay. Maybe in the future we find ways to shift class initialization, but that's not where we've gotten to yet. And for all the reasons you're saying, there's a lot of challenges there. It's very easy to capture the environment. And even in things that you don't expect to capture the environment. So Java util collections, for example, a lot of them go and check how many processors your system has and uses that to optimize the layout across the concurrent data structures. Well, if you cache that from build time, that might not apply at runtime.
Yeah. Generated things architecture specific at this point? Or you still waiting on just doing things that are architecture generic and letting JIT handle the architecture specific stuff?
So right now we've been doing things that are architecture specific. So the code that you're running is specific to the machine that you're running it on, or at least that architecture. Hotspot has flags and tuning so you can make it less machine specific, but we haven't played with mixing those two things together yet. There may be a piece of that down the line. We've been looking at how fast can we make this start. When you go to deploy these things more widely, you may want to have the AOT, as you said, be sort of a little more generic, and then have the JIT do the top-ups on the system-specific areas. Thank you.